Hopper. She's a just started PhD student, and she's going to tell you what she has been working on in the context of the master thesis. Alessandra has worked with Steve Campbell in University College Dublin, and yeah.
Okay, thank you. Hi, I'm Alessandra from ourselves. I would like to be presenting today my work, my thesis, my master thesis, in which we focus on studying or to reveal non-classical nature of single molecule magnets. So, before diving into the single molecule magnet, I'd like to talk about the concept of non-classicality. It's not working. That we went through.
It's not working?
No. The other is working, so.
But
Wait, I can try one.
not working. I think you just have to use the...
Okay. Okay. Can I go up to this one? No. Okay.
Yeah.
Okay, so before diving into single molecule magnets, I would like to talk about the non-classicality that we want to aim, that we want to detect. As we know, the border between quantum and classical is not easy to trace, and in the early days of quantum mechanics, people tried to consider the quantum world and the classical world as a sort of separate entities. And this was okay at the beginning, but now we know that we want to exploit quantum resources, and to do so, we need to recognize quantum objects, quantum states, and in some way use them. So, in order to do so, in order to to understand the concept of non-classicality, we want to answer the following question. How do we know if an object is non-classical? So, observing an object, how am I supposed to study this object to understand, to infer some non-quantum nature? To do so, we decided to try to study the way in which this object interacts. And we use the following, we exploit the following result obtained in this paper. In this review, the authors were able to study, to reveal non-classicality in an object that we cannot over which we cannot perform direct measurements. The idea is the following, and I would like to briefly outline the main points of this result. We have three subsystems. So we have the system A, C, and D. The system C is our mediator or the inaccessible object. It's an object that over which we cannot perform direct measurements, and we want to investigate this object in order to understand if it has a non-classical nature. Then we have the system A and the system B. We have control over the system, these systems. We can call them probes, and we can perform measurements on this object. The idea is the following. If I start from a product state of these three systems, and then I let the global system evolve, if I observe entanglement between the system A and the system B, so if I observe a gain in the entanglement between the system A and system B, then I can affirm that the object C is non-classical. So, let's see why I can say this thing. First of all, we are going to use the following theorem that it is proved in the review. And actually, the theorem states that if I observe that the entanglement between the partition A and the partition B and C at a certain time t cannot increase during time if the discord, the quantum discord, which is a non-classical correlation between the system C and system A, is equal to 0 at any time t. So, this is not enough, because in this theorem, as you can observe, we are treating the entanglement between the partition A and BC. But as I said at the beginning, we cannot perform measurements on C. So we need to, in some way, we can compute only the entanglement between A and B. For this reason, we add a second result, a second correction that we are going to use, which is the following. The entanglement between the partition A and the partition B is always less than or equal to the entanglement between A, the partition A, and BC. What does this mean? If I start from the following condition, so if I assume that at time z, the entanglement between A and B is equal to the entanglement between A and C and B, this means that if I observe an increase in this entanglement, then also this entanglement has increased. And for this reason, due to this theorem, the discord between the system C and A and B is different from 0 during the evolution. Now, we have understood that if I observe again the entanglement between the subsystem A and the subsystem B, I have quantum discord with C. But why this is linked to the non-classicality of C? As we know, the concept of quantum discord is related to the non-orthogonality of states. So, by definition, quantum discord can be characterized by the mutual information, in which we have the total correlation between two subsystems, in this case A and B, and the classical correlations. This quantity in a classical system coincides, so the discord is 0. But in quantum system, as we know, if we perform measurements on a quantum system, the system is disturbed by this measurement. So, this is the concept of quantum discord, and the presence of quantum discord implies non-orthogonality of states. So, indistinguishability of states that we are going to characterize as our concept of non-classicality during our project, during our work. So, now that we have clarified the concept of non-classicality, I hope so, that we are going to looking for, we can move to the single molecule magnet itself. I would like to say something else about this criterion, and the fact is that it works very well under a set of minimal assumptions. So, for example, the object may remain inaccessible at all times. I don't have to detail the interaction between A and C or C and D, and every part can be open to its own local environment. The important aspect is that A and B do not interact with each other, but only through the interaction with C. It can be applied on a series of different situations. For example, in quantum optics, where, as we know, quantum states are fragile states, so we don't want to disturb them with measurements. And also in quantum science, where we often have to deal with complex systems or hot and dirty systems that we don't know how to describe in detail, or which interaction is difficult to model. And hypothetically, we can also use it to infer the quantum nature of gravity using two massive probes. In our case, we want to apply this criterion in order to investigate non-classicality in single molecule magnets. So, to do so, we need to create, model appropriate, a suitable working setup. So, let's see. Okay. First of all, why molecular magnets? Molecular magnets are particular molecules, organometallic molecules, characterized by a high-spin magnetic core and surrounded by carbon ligands. And the interesting part is that they present both quantum and classical features. So they actually sit at the crossroad between the two regimes. And they are also useful because, as we know, nowadays we are trying to encode information, to protect information against decoherence. A way to do so is by creating, developing new protocols using quantum error correction. And to do so, we need logical qubits, so objects that have more than 2 energy levels. And molecular nanomagnets seems to behave as perfect or ideal platform to as working as physical qubits. Also, they are useful in quantum sensing and regular spintronics. And another aspect I would like to outline is that if we modify the chemical structure of single molecule magnet, we can modify their properties. So maybe I'm not able to do it, but chemists are able to modify the structure of the single molecule magnet in order to meet some conditions. For example, modifying the temperature at which I can observe quantum hysteresis and other properties. So the first problem we add to yeah, usually it's nanomagnets, so from 1 to 10 nanometers. Very, very small.
How many atoms do you
I don't know actually how many atoms.
And these are ordered structures?
Yeah, they are the structure thanks to the carbon ligands, because they are the carbon ligands to the single molecule gives to the single molecule magnet another structure. So we have symmetry. It can be like isotropic, rhombic, or axial. It depends on the structure of the single molecule magnet. Okay, so the first problem we had to take into account was how to model these single molecule magnets. As a single molecule magnet, we are presenting one of the most studied single molecule magnets, which is called Fe8. And as you can observe, the first interesting part is the magnetic core. So, if we assume that we are working at low temperatures, we can describe the high speed. We can, in some way, we can neglect the interaction between the single ions and treat these different ions as a giant spin. This is because at low temperatures, the molecular ground state is well separated in energy with the excited states. So I can actually model my high-spin magnetic core in this way. Now, the method that describes this giant electronic spin is, of course, a term that takes into account the fact that the giant spin reacts to an external magnetic field. And then other two terms, they are also called zero field splitting Hamiltonian. These D and T are physical parameter, and in particular they are called anisotropy constant, D. This is axial and this is transversal. And these two terms take into account the fact that the giant spin is characterized by nonlinearity or nonlinear structure, and so anisotropic behavior. Okay. As you can observe, we were able to model the high-spin magnetic core, but we would like to describe also the carbon ligands that characterize this single molecule magnet. So in order to do so, we use the following model. Before doing this, I would like to show you what's the impact of these two terms in our energy level splitting. The interesting part is that even if I'm not applying an external magnetic field, the anisotropic nature of the spin of the Hamiltonian split the levels. So, for example, S equal 1, in an anisotropic situation, these three levels are degenerate. With axial or rhombic symmetry, instead I have a splitting these levels, even if the magnetic field is 0. Now, as I said at the beginning, the single molecule magnet is characterized by its high magnetic core and the carbon ligands. And furthermore, we assume that the single molecule magnet is immersed in a solution. So I would like to model the solution and the carbon ligands. And to do so, we decided to use a nuclear spin buffer. So we assume that the single molecule, the giant spin, can be all the ligands and the solution can be described by this buffer. So we needed to add some terms to our Hamiltonian. The first three terms take into account the fact that each nuclear spin reacts to the external magnetic field. Then we have beta and delta. These are physical parameters that describe the interaction between the spin that constitutes the buffer. So, for example, we could have a strongly interacting nuclear spin bath or weakly interacting nuclear spin bath. And the other two terms, so alpha and gamma, takes into account the interaction between the giant spin and the nuclear spin bath through hyperfine interaction, which is actually the predominant effect that can cause the coherence in our spin. So this is our Hamiltonian. So this is I would say the Hamiltonian that describes in a more realistic way the single molecule magnet. But of course, our target is to apply to understand if the single molecule magnet is has a quantum nature. So we want to apply the criterion that I presented at the beginning of the presentation. So I'm going to do so. So I hope that I hope it's clear that the single molecule magnet is our inaccessible object. So we are missing the two probes that we need in order to study the entanglement or the gain entanglement. And to do so, we decided to put the single molecule magnet inside a multimode-driven cavity. So this is the setup. And the Hamiltonian that we had to deal with was the following. So we had some terms related to the bosonic operators that characterize the energy level of the modes. Then we have the interaction between the single spin, the giant spin, and the mode. And all this Hamiltonian describes the single molecule magnet itself, and then we have to the drive, the external drive, characterized by some lasers. The problem was that it wasn't easy to deal with this Hamiltonian because here we have bosonic operators and spin operators. So we decided to apply two different approximations to simplify our discussion, and we decided to apply the first thing we decided to treat the nuclear spin bath, so the ensemble of spins, as a collective giant nuclear spin. And this was reasonable. And the second approximation was to apply Olsen-Primakov transformation, which is a map that goes from bosonic operators to spin operators. And we are working, as I said at the beginning, at low temperature, so just the lower energy levels are populated. So actually, we are not interested in what happens in the higher energy levels. And so this seems to work. As you can, when we apply these two transformations, the Hamiltonian assumes the following form, which is not so much better than the one before, but at least we can work with bosonic operators and apply the well-known laws of harmonic oscillators. So I would like to dig a bit into all these terms. And as you can observe, first of all, we have two nonlinear terms. They are quadratic. We call them nuclear terms. And then we have the spin-forking coupling, which is a sort of beam splitter coupling. The hyperfine coupling between the giant spin and the nuclear spin, the joy, and a squeezing term linked to the nonlinearity nature of the single molecule magnet. As a first approach, we decided to neglect some terms that were order of magnitude lower than the energy levels of the bosonic operators for the modes and for the spin. And in particular, we decided to neglect the pair terms and the back-related terms. So the Hamiltonian, in what we called a zeroth order approximation, assumes the following form.
Sorry, can I ask a question before you? I did not see the word question. So what it says, what it says.
Yeah, of course. A is the bosonic operator describing the cavity modes. S is the bosonic operator that describes the giant spin, so the magnetic core of the single molecule magnet.
Which is a bosonic operator?
Yeah, because I have perfect. And then we have N, which is the bosonic operator that describes the nuclear spin bath, because we assume that the ensemble of nuclear spin bath can be approximated as a giant nuclear spin. And this giant nuclear spin can be then mapped to a bosonic operator thanks to Olsen-Primakov. So actually, it's the same with the electronic spin bath.
So you're basically assuming that you have your giant spin is capital S, is
Yeah.
very big, or just
Not really. I mean, for example, in the case of Fe, so the nanomagnets that we studied, is like S equal 10. It can be also S equal 80. It depends on the nanomagnets that you're using. But in this case, it is S equal 10. So we are working with like 21 levels.
And do you have an estimate of the temperatures you need to work on?
Yeah. Actually, we should stay lower than 30 Kelvin. So it's this is the for the F3, of course, because it depends on the value of D and E. So maybe it can be changed thanks to chemistry.
Could you also repeat why you are talking about the nonlinear just
Yeah, it's a first approach because we need to do some calculations. So we decide to work with this simplified form of the Hamiltonian, but then we neglected some terms that were lower as order. So we will see that it's reasonable at the end of the discussion. So with this Hamiltonian, we decide to we compute the Alexandra equational motion. Yeah, of course.
Sorry, dropping all these terms,
Yeah, exactly. It's like I'm just in this first approximation. It's like I'm describing a single molecule magnet, just a giant spin, which actually is not realistic, of course, because it's like I'm not taking into account the decreasing effect of the buffer, so the carbon ligands and the solution, and the nonlinearity of the spin, which characterizes the single molecule magnet itself. But it's a first approximation, and then we. So.
The coupling between the big spin and the cavity is strong.
Sorry, can you?
The coupling between the big spin and the cavity is strong.
Okay, this is an interesting point.
If you can calculate it in terms in the last term of the first one.
Okay, about the coupling between cavity modes and spin, the point is that they are interacting through the magnetic component of the electromagnetic field. So this is not so strong. So it's like, for example, the value that we used for our original point of view was 10 megahertz. But the point is that we prefer not to go to counterrotating terms because these terms, which is the drive, is linked to different value of lambda, and because it's equal to the frequencies of the cavity modes. So we prefer to maintain it just for. It's not so easy to go to a rotating frame due to the form of the Hamiltonian, and the fact that these terms have different value of lambda for this sum of. So we use this Hamiltonian, we compute the Langevin equational motion through the Starman procedure. Then we write this Langevin equational motion through quadrature operators. And the point is that I can obtain a drift matrix and compute the covariance matrix. So the important message from all these operations is that I can compute from this Hamiltonian the covariance matrix. And I can use this covariance matrix to compute the entanglement. In particular, I would like to, the following. We assume that in the cavity modes we have 6 modes. We assume that in the cavity modes we have 6 modes. And these modes have different frequencies. So they are not interacting with each other. And this is important because we need to this condition to apply the criterion. Then we divided these modes into 2 groups. And we assume that this group is our probe A, and this group is our probe B. Using the covariance matrix, we can compute the entanglement between this group of modes and this other group of modes. And the result that we obtain is that we observe a gain in the entanglement. So this is the entanglement between group A and group B. They are not interacting with each other, but they are interacting with the single molecule magnet. And for the criterion, this means that in our first approximation, the single molecule magnet has a non-classical nature, so has some quantum features. As I said at the beginning,
Does this feature that you said depends on the calculation that you're choosing?
this feature.
This graph that you're showing of the entanglement over time, does depends on the partition of the that you're choosing?
The quantity of entanglement depends on the partition, but not in a very significant way. So I tried more partitions, so for example 2 and 4, or in a different way. And we decided to take the partition for which the entanglement was maximized. That what we discovered was it was always the same things to do. So the first mode will be the last ones, and all the other modes in the middle with another group. So we try different partitions. But at the end, the point is that we are not really interested in the amount of entanglement because we don't want to exploit it. We just want to see if there's a game in entanglement. No, there's no partition for which. No, absolutely. For all the partitions that I tried, the entanglement was different from 0. So, as I said, this is a 0th order case, so it's not so realistic, and we decide to reinsert in the Hamiltonian the buff term. I'll show you which word.
Sorry, why did you say 6?
What did you say? Sorry.
Why 6?
6 modes, yeah, because it's like at the beginning we tried to see which was the optimal number of modes. The point is that we observed that over 6 modes, the entanglement saturates. It's like even if I have, for example, if I have 10 modes, I don't obtain a value of entanglement which is higher. Actually, I can observe also a decrease in the entanglement, and we thought that this is linked to the fact that the entanglement is caused by the single molecule magnet. So this is my source of entanglement. So I don't expect that adding modes which do not interact with each other, the entanglement can increase further beyond a certain level. And also due to the fact that if I add more modes, I have a different partitions, and there's a...
My question was like, why not just 2? So
okay, because it's not really the convenient for a quantity. I mean, it's like the entanglement is non-trivial. There's also entanglement, but to improve the way in which you see entanglement, 6 modes is the perfect way to see it. In the thesis, I think we show for 2 modes and 4 modes, and we show that 6 modes is the best way to represent it. Yeah, you see entanglement different from 0. It has a different form from the other, of course, but entanglement is always different from 0. If the lower is less, of course. Also, of course, yeah, the lower is less, but there's entanglement, and it's different from 0. Which makes sense, I think, because the nature of the single molecule magnet shouldn't depend on the number of modes that I have in the cavity. So.
Sorry, one thing I don't understand is what do you mean exactly when you say that 6 is the best? Like best in which?
That's because it's a way to it's the number that maximizes the entanglement, but it's also the less number of modes that I can use. Of course, if I add more modes, I have to deal with infinite. I mean, the space becomes bigger, so it's not really nice. Yeah.
Did you optimize the entanglement or the entanglement gain?
No, the entanglement gain or the entanglement is the same because I think because I start from 0. So I observe the peak, the maximum value of entanglement that I can reach for each partition.
But do you expect more in the game?
Yeah, in the game. I'm interested in the game. Also because we start from 0 entanglement. So starting from 0 entanglement, gain or observing entanglement is. Okay, so you're saying that, yeah, of course. No, we observe the gain of entanglement, so the maximum value that the peak we can, I can show you. No. The peak of entanglement in the graph. This is the quantity that we considered, and also the entanglement that we observe at steady state time, so a long time. Then we add the buff inside the Hamiltonian to see what happens to our entanglement, and we obtain the following result. Of course, we compute the Langevin equation and the covariance matrix. And sorry. Wait a moment. Okay, and this is what we observe. So the yellow function is for the zeroth order case that we have seen before. The first order is when we add the coherence effect of the bond. So we observe a value of entanglement which is lower than the one before, but there's still entanglement. So for our criterion, this is sufficient to say that the single molecule magnet continues to have a non-classical network, present non-classical features. It's also interesting to see what happens when I vary this constant, which is the constant that takes into account the interaction between the high-spin magnetic core, so the giant spin, and the buffer. In particular, starting from a value of 10 to 6, the difference is almost trivial. I mean, they are equal, they are compatible. Then I increase this constant, so the difference is not really significant, 10 to 8, and just when I reach 10 to 9, which is the...
I'm sorry, why does it also look like even though they correspond?
Why? I think that's, I don't know, maybe because it's like, it's like the way in which entanglement does, I think. We didn't really, because it's not important, I think, for our analysis. So we didn't look into this aspect, so the selection of entanglement. Maybe it's interesting to see why it does this way, but for our scope, the point is that there's entanglement, yes. There's again entanglement, yes, so can use my criterion. Then also there were some interesting aspects also for the steady state value, but this is something that maybe we can do in a later time.
So first order means including all the nonlinear terms, right?
No, first order means when we include the buff terms.
Okay.
So in the first, because I had the zeroth order in which I remove everything, now I have the first order in which I add the buff-related terms. So now my single molecule magnet is described in a realistic way because I have the electronic joint spin and the nuclear spin buff, carbon ligands and solution. But I'm treating the spin as it does not have a nonlinear nature. This is the...
So what like in the sense of
No. Yeah. It's not, no, there's no perturbative. So, alpha 10 to 9, if I increase the interaction between the carbon ligands and the high-spin magnetic core, I can obtain value entanglement similar to 0, which seems reasonable because it seems that the strong interaction between the electronic spin and the nuclear spin are like destroying the quantum features of the giant spin and single molecule magnets itself. Now we can move to the second order case, which is the last case. We reintroduce the nonlinear terms. This was these two, K1 and K2, the pair terms. And the point is that, as I said during the presentation, we compute entanglement using the covariance matrix, which is a useful tool as long as I'm dealing with Gaussian states. But if my Hamiltonian presents non-linear terms such as this one, we're not sure that the system evolves preserving Gaussianity. But we want to use covariance matrix. So we decided to proceed with a linearization. We computed the Langevin equation from this Hamiltonian, which are nonlinear, and then we proceed with a linearization using a method that is common in optomechanical systems, in which we assume that the Gaussian operators can be written as a mean value plus fluctuation. We did several calculations to find this value and the fluctuation, and then we linearized the Langevin equation of motion. Once we linearized the Langevin equation of motion, we could compute the covariance matrix and the entanglement as we were used before. Yeah, as we did before. And this is the result that we found for the FE hand. So The yellow line that is highly compatible with the green line is when the single molecule magnet is treated as a giant spin. Then we have the buffer, and this is the red one. And now I'm adding also the nonlinearity of the spin. And entanglement, the gain in the entanglement is different from 0, so I can affirm that my single molecule magnet is not as a non-classical measure based on the criterion. And also, since, as you can observe, it's like adding the nonlinear terms, I'm contracting the Green's effect of the bottom, if they are highly compatible, the 0th order and the 2nd order. So we decided to study another single molecule magnet to see if the effects were similar. And the point is always the same. The nonlinearity works in this way, but as I said at the beginning, we focused on the fact that the entanglement gain is different from 0. So also in this description, which should be the more realistic one, the single molecule magnet has a non-classical nature. Now, at the end of all these results, we wanted to test the robustness of our results, and we decided to move into density matrix description. Oh, yeah, okay. So we use the following phenomenological density matrix, where we have the Fourier convolution with the Hamiltonian here, in which we use the Brewer Hamiltonian. So we didn't perform also empirical approximation. We didn't use the linearization or omission of terms. And then we have the pure phasing for the giant spin and the dissipation for the cavity modes. And now the problem with the density matrix formalism, the problem was the dimensionality of the space in which we simulated the dynamics. Because of course we are working with S equal 10 spin, so 21 levels. And then we have 6 cavity modes. So we needed to pay attention to the window in which the two methods were manageable and feasible. And we obtained the following results. So the entanglement between the density matrix approach and the covariance matrix approach is compatible. And in particular, we observed that if I increase the value of nonlinearity, in which I take into account only in the 2nd order case. For example, here I multiplied for a factor of 3. The only case in which I continue to maintain the compatibility, it continues to be compatible with the density matrix is the 2nd order case. So showing that it seems to be robust to the approximation that we did to the 2nd order case. And this concludes all the things that I did. Yeah, because I decided to, for example, this entanglement is not the real entanglement of the single molecule magnet that I studied before, because I had to consider a single spin equal to, and and the cavity modes I use power that allows me to do a reduction of the cavity modes levels, and also I had to consider a window of time very narrow, because of course then and that's it. This is the conclusion. Something to see and classify the single molecule magnet cavity, and then we studied entanglement. And all the results that we obtained seems to suggest a classical nature of the single molecule magnet. And we continue the study also in the PhD project, trying to look at this, to answer to this question using reservoir dynamics or machine learning. And that's it, I think.
Can I ask, I didn't quite understand this. So, in the first part, you discussed the fact that you want to use these probes to assess classicality, meaning the entanglement, I guess, of the system itself, which is the giant.
The giant.
Right. So the entanglement you showed in the plots in the last part is the entanglement that kind of leaked from the system itself to the probes, right?
I wouldn't say so. I would say that the entanglement that is the gain entanglement that we observe implies that the system C needs to correlate in a non-classical way. But at the beginning, we do not have entanglement because we start from a product state between system A, B, and C. So the gain entanglement is linked to the gain entanglement for me means that the system C correlates in a non-classical way during the evolution, and this non-classical way creates or implies the presence of discord, and the discord implies non-orthogonality of states, and so this is the non-classicality notion that we are looking for in the single molecule magnet description.
And can you back to the picture, the last picture? Anyway, so why do you like?
Which one, sorry?
You have, that one's fine, like ABC, the one before.
Okay. Okay, sorry. This one.
Yeah. Like, why do we need two different systems as a probe? Or is it just like a fair thing? Like, we actually need two systems that are distinguished as probes, or it just mean the system is C and then I have a probe which might be in the department and etc. Like, because the way you
I think that this is because we want to highlight the fact that this system C we cannot perform measurements, while A and B we can control them, we can prepare them in a particular state, we can perform measurements on them, and so we call them probes.
But like, you need two probes, or you just need one probe that is in possibly many systems?
We need two probes. In fact, we could also use, for example, six cavity modes and use 6 cavity modes. Instead, we needed to divide them into two groups, and this is linked to the criterion itself because it's used for when I show the here. No, okay, here the criterion is based on this theorem. So, in order to be, let's say, coherent with what we so. I could have also used a mode, another mode, and neglecting all the others.
Okay, so the choice of this particular way of assessing nonclassicality is like particularly suitable for these kind of systems, or just something that was tried in these systems?
No, it was particularly useful for us because in this way we could study the single molecule magnet without acting on the single molecule magnet. So it was a way to apply this criterion, and also it has been applied to other systems, for example, photosynthetic organisms or quantum optics, or also for the quantum nature of gravitational forces. And it seems to work very well, so we wanted to use this theorem. Of course, there can be other ways to do it. For example, some in pharma, they did a paper recently, and they are studying the non-classical nature of single molecule magnets, seeing if they violate Bell inequalities. So, this could be another way.
Actually, another question. So, what's the actual state of the art in this kind of systems? Like you mentioned, they want to use them as fuses.
Yeah.
So, like, can you easily control them, like Bill Gates?
I think so. In particular, like physicists like Cammarata or Chiesa in pharma, they are working to try to understand if they can create quantum processing, quantum processor with single molecule magnets. So actually, they seem pretty promising as physical platforms. Then, of course, we will use. Also, for the paper that I use here, chemists are working to model this system in order to predict particular features. So I think this is a very recent, 2024 this year, no, 2025 exactly. So it's